you go. Yeah, before this semester, I would do this also during the lecture time, and then I always find myself, really just struggling for, more time at the end of the semester because, all this stuff is taking up quite a bit of time in the lecture. But that's why I'm doing this, during the lab time. Okay, which program do you want me to work on first?
Number 2.
The second one?
Yes.
Buggy 2? Okay, let's work on Buggy 2. So I'll just do a right click and save link as, because it's a C source file already. I don't need to copy and paste it this way. And I'll use this window to go to the folder, and we'll go ahead and take a quick look at Buggy 2. Okay. Buggy2.c. And I'll let you guys tell me what do you think is wrong with this program. I think it's accessing an array out of bound. Okay, so on line 5 there's only one problem with this program, which is on line 5, because on line 5 I am adding 4 to the element at index 16. But that really is the 17th element because we count from 0. So that means, this instruction or this statement is not really changing anything in the array itself. It's not in the allocated portion of the array. This is 1 byte right after that array. Well, what do we use memory for, after, a local variable array? Well, the previous class probably did not tell you anything about that, right? We just know that there's some memory location. We don't know what it's useful for, but we know for sure that it's getting changed, okay? Maybe it's not really important, okay? Let's hope it's not important and nothing bad is going to happen with this program. Okay, so let's go ahead and, compile this program. GCC-G so that we can turn on debugger symbols. -C for just compiling and not linking, and buggy2.c is the source file. This will give me an object file, and then we can now link the object file to the executable, which I'll just call buggy2, and it will use buggy2.o as the object file, which is serving as the input to the linker, and that will finish the linking. All right, so I'm going to run the program. Okay, because I'm just hoping that this program will still work, even though we kind of know that it has something that is questionable.
What's the switch G do again?
-G means it will turn on debug symbols, and it is useful for GDB because without that I cannot do source level debugging. With this I can do source level debugging. Okay, so the program prints 2.5. Let's go ahead and take a look at the program itself. No. .c, right? And we'll just run it again. All right, so now we have both, a listing of the program and also the output of the program. Well, the fact that it has a segmentation fault, which is a crash, is not surprising. Okay, after all, we did trash, some memory that we are not supposed to, right? That can always lead to a segmentation fault, which is basically just telling you that you are trashing, you're modifying some memory location that you're not supposed to. That's all segmentation fault means. But what is mysterious is before we get to the segmentation fault, when we print out Y and Z, it is printing out X and Y instead. Everything is shifted by 4 bytes. Okay? Well, that is... Can you explain this using what you have learned in cisp310? How about 400 for those of you who have taken cisp400 or 430? None of those classes will tell you why this program behaves like this, but it does. Now, when you look at this program, you go like, well, this is a handcrafted example of crashing a program in a questionable way. Well, guess what? It does happen in real life as well. Except in real life, you're not going to deal with a 18-line program. You have an 18,000 line program that has a behavior like this. When you get into the debugger, everything is shifted by one variable, and you have no idea why that is the case. Okay, so the focus today is to use GDB. So I'm going to get into GDB. So we'll GDB, and then you specify the name of the executable so that we can debug this program. Okay, the first thing we do is we know that by the time we get to the printf, something bad has happened already, right? Because if not, we should have been printing 5 and 1 and not 2 and 5. Is that okay? So whatever is triggering this problem, whatever the cause of this problem is, has to be before the printf. Is that okay? All right. So what we'll do is we'll put a breakpoint. We'll list the program. Use the command L in GDB to list the program, and then until we get to the line that we want to stop. So we'll put a breakpoint on line 18, okay? Because line 18 is the printf statement. Maybe printf is implemented incorrectly, and that's causing the problem. I'll also put another breakpoint on line 17, okay? And the reason why I put it onto line 17 is because I'm suspecting everything up to line 16 is still okay. It's just a whole bunch of assignment statements. Doesn't seem like anything should have gone bad, quite that bad, at that point. So I'm suspecting it is the function call that is causing the problem. And by the time I get to printf, things have gone wrong already. So I'm putting 2 breakpoints into this program, and I'll go ahead and run it, R to run the program. And when it hits the first breakpoint on line 17, it pauses the execution of the program. So right now, the program is quote-unquote active, but it's not running, okay? So I have all the variables initialized, and I can examine the variables at this point. So I say print x, okay, x is 2, which is consistent with line 14 of the program. We'll print y, 5, print z, it is 1. Extremely boring, right? There's nothing to this part. Then we'll single step. Now, it is important to do a single step here because a single step will let you get into a subroutine that you're calling. The other one is called next. If you use next or n, it will execute the subroutine f without stopping in the subroutine itself. So I do want to stop in the subroutine, so that's why I want to use step here. Now we're inside the subroutine. It only has one single line that changes the location x bracket 16. Well, I'm just gonna print it out first and see, okay, what exactly is at that location. Some really kind of oddball number, okay? Now when it prints it like this, this is the decimal interpretation as a signed number, and this is an octal number corresponding to the bit pattern. Yep.
Now, say we're following along, and there's like a 12 times.
Repeat 12 times. Are you printing x bracket 16 or just x?
We just print it. Oh, gosh.
I'm printing only one character. Okay. So then I single step this. Okay, I single step this, and I print x bracket 16 again, and well, it did what it's supposed to, right? Because I added 4 to negative 104, and I get negative 100. Seems to be okay with me. And then I single step. We are already at the end of function f. So when I single step again, I'm going to go back to the main subroutine. Now I'm suspecting the print itself or printf itself may be buggy, and that's why it's not printed correctly. So I'm going to use the debugger itself to print what is x. Whoa! Hold on a second here. X is supposed to be what? 2. Print y. A. Y is supposed to be 5. It is now 2. And z is supposed to be 1, and it is now 5. So the problem does not have to do with printf. Printf did not do anything wrong. For whatever reason, these things have changed their values. If I have a few assignment statements in function f maybe, just maybe, that will kind of modify the variables over here. But I only have one single assignment statement, and it should have changed just one single character. It cannot change 3 4-byte integers all at the same time. Is that making any sense to you? So that means, hey, something else is wrong here. I'm going to rerun the program with exactly the same breakpoints, but this time I will look at the address of the variables. Okay. So I'm going to run the program again. Whenever you say R to run the program, it will rerun the program from the beginning. It will abort the current session and start the program all over from the beginning again. And it will confirm because I'm still in the middle of a session. So yes, I do want to restart the debugger and start from scratch. Now I'm right before calling F. So instead of just looking at the value of X, I'm going to say, tell me where it is. And tell me where Y is. And tell me where Z is. Okay, fine. We have, these are locations in hexadecimal. When you specify a number in hexadecimal, which is base 16, now remember, in base 10, how many digits do we have? 10 digits from 0 to 9. In binary, we have 2 digits, which is 0 and 1. In base 16, guess how many digits we have? 16, from 0 to F. So we basically use 0 to 9 to represent exactly 0 to 9. But 10, what we know as 10 as a base 10 number, is represented by A. What we understand as 11 in base 10 is B, and so on. So 15 is F. And that's with one single digit in hexadecimal numbers, which is base 16. Now, we'll talk about base 16, why it is so cool and so useful, and it is related to binary numbers in a very interesting way. But for the most part, they're just like regular numbers. Okay. You can see that all of these things start with a 9 and an 8. So it's the least significant digit that is actually significant. C is 12, 8 is 8, 4 is 4. They're all off by 4 bytes. Does it make sense to you that these addresses are off by 4 bytes? Yeah, they make sense because each variable is a 4-byte number. Yep, go ahead.
The interesting thing is, why did they create Z first?
Huh?
Why did it allocate a space that's before?
Okay, that's a good question. So the question was, why the compiler is allocating a lower memory location for Z as opposed to X, which has a higher memory location.
Yeah, which was created first in the code.
Which was declared first. Right. Mm-hmm. Okay, so that question has to do with how a stack works. We will definitely get into all that stuff later on, but it has to do with how a stack grows. A stack, when a stack is empty, it has a high memory location, or the stack pointer has a high memory location. As we push more stuff onto the stack pointer goes lower and lower. So this is actually just following that order. If you declare a variable later, it will be consuming space later on, and the later space has a lower location.
Okay, so technically I was still, or X was still created first.
Right, yep. Okay, we already know what F is going to do, okay? Nothing really interesting, doesn't seem to be doing anything wrong. So I'm going to do a next this time. In other words, I'm not stepping into function F, I'm going to step over function F. And now we are about to execute line 16, okay? F is all done. So let's go ahead and print the addresses of X, Y, and Z again. You guys don't seem surprised or amused at all. Is that because of the lack of blood glucose? Because you guys are all hungry and just waiting for dinner? Because I would be surprised. It's like, what happened here? How come the addresses of X, Y, and Z have changed? It's not the value that has changed. It is the addresses that have changed. Okay? And it's all caused by what? The subroutine accessing 1 byte out of boundary. And all I'm adding is just 4 to it. And that 4 is corresponding to how the actual offset of these things.
So the number 4 itself is just because they're both integers, they're all integers, and that's 4 bytes.
Right.
If you made it 8, it would exhibit something different.
Yes. Yep. The addresses will end up off by 8, but if it's off by 8, then you will see some kind of garbage value. It won't look as cool anymore. All right. So remember this example, because we will see this again at the end of the semester, and then at that time, I'm hoping all of you will feel comfortable and say, we know exactly what is going on the stack, and it is completely predictable why the program is doing this. Because this is allowing you to debug a C or C++ program by looking at the symptom and say, hey, just looking at this symptom, I know somebody is messing around with the stack, accessing something out of bound and messing up something else on the stack. Now, what that something is, I cannot say it now because we don't have the background knowledge to understand that part yet. Okay, but we will do that. But just using GDB, we kind of know that F did something. Okay, so I'm going to rerun the program yet one more time from the beginning. But this time, I'm going to single step into the subroutine. So what I'm going to do is to say, right now we are in the subroutine F, which is called by main. But what I want to do is, at this point, I want to know what is the address of variable x in main. Well, that's kind of difficult to do, because if I say print, actually in this case it will work for x, but it won't work for y, because y is in the wrong context. Y is a local variable of main, it is not a local variable of f. And because I'm currently in f, I have no visibility of local variables in main. Is that making any sense? Because I'm still following all the rules of scoping in C and C++ programming of local variables. Fortunately, GDB has a feature called BT, which stands for Backtrack. Backtrack is really useful because it shows me that we are currently in frame, quote-unquote, frame 0. We'll explain what a frame is in details later on. But for now, a frame is one invocation of a subroutine. Okay? We're in frame 0, which is F, and frame 1, which is one frame away from where I am now at, is the main subroutine. Now, with this in mind, in GDB, you can say frame 1. Okay? This one is corresponding to the #1 of main. In other words, I'm now switching my context from subroutine F to main. And it will confirm that, okay? Now that I'm, confirming that I'm in the context of main, now the execution point is still in F. It's just that, from the perspective of what I can inspect, I'm now back to main. So I can now say, oh, tell me what is the address of Y. Okay, it's the same one as the one before things got messed up. Okay, and I can say what is the address of Z. Okay, everything seems to be good. Okay, so now what I will do is I'm going to single step in subroutine F. Okay, we'll execute that one single assignment statement in F right now. Single step. I don't have to switch my context back to F to single step because I only have one point of execution. And whenever I single step, it is always using that one single point of execution. So single step. Now I'm hoping I'm still in the context. If not, I can always say frame 1 again. So this will put me back into the main subroutine. And I'm gonna print the address of Y again, and it's already messed up. So even though I don't quite know why that one little assignment statement in F can cause such a big problem, I have just zeroed in to that one line that is causing the problem. Is that making any sense? Kind of? Maybe? I want my dinner? All right, so these are the tools that you have in GDB to help you debug a program. If you're still taking CISP 400 or 430 this semester, you can use the technique that you learned in 310 and apply those techniques to your 400 and 430 classes. All right, so that's the first program, which is kind of resolved. We know where the problem is. We have pinpointed the one single instruction that is causing the problem, and we confirm that. Let's take a look at buggy 1 instead. Okay, this is buggy 1, and what I'll do is I'm going to download, and we'll go ahead and compile and run this program. So this is buggy 1. We'll do a gcc-g-o, -g-c buggy 1.c, and then do the linking buggy1.o. Oops, specify the output name first, and then buggy1.o, which is the object file name. And it's already given me a warning. Okay, the linker is is complaining and saying, hey, the get function is dangerous and should not be used. Danger. I'm just gonna ignore that. I'm a human programmer. I know what I'm doing. Right? All right, so let's go ahead and run the program. Run buggy 1. And its job is supposed to reverse strings. Okay, you give it A, B, C, D, it will come back as D, C, B, A, and it will work, with whatever you can type in a line. So we'll just try it out. Okay, tag comes back as cat. Okay, well, that's correct. 1, 2, 3, 4 comes back as 4, 2, 3, 1. And if you give it a longer input, it gave me a segmentation fault. Okay, so that means I'm accessing memory locations that I'm not supposed to. All right. So this program works a little bit, and then it fails in certain test cases. Now, if you specify exactly the same input again, it will fail exactly the same way. So I'm just gonna copy and paste this, as my output here, and then press the Enter key, and it fails exactly the same way as last time. That is good. Okay. If you have a problem where the program fails differently, even though you give it exactly the same input, you have a much tougher problem than what we're seeing here. Most of you hopefully won't have to deal with problems like that, but if you write device drivers, any type of interrupt subroutines or multi-threading programs, you can run into situations where the same cause, the same bug, the same defect in your program can cause different problems, and sometimes it will seemingly just random. The program will work just fine for a few days, and then it will crash. Next time it will run for a whole month, and then it will crash. Next time it will run an hour, and then it crashes. And every time it crashes, the symptom will be different. Okay? Question? Oh, okay. All right. So we want to get into the debugger. Okay, so we will say gdb buggy1, and it has a segmentation fault. So the first time we're going to do it is just to run it like this, no breakpoints whatsoever, and just make it break. All right. So we now have a segmentation fault, and what you're seeing here is it is attempting to execute at location 0. Okay? For whatever reason, it's trying to execute at location 0, which is not good. Location 0 is not a good place to go if you want to, run and if you want to execute an instruction. Okay. All right. So we don't really quite know in the source code, where we are having this problem with, where the problem comes from. So it's time to go, list the program a little bit here. This is the entire main subroutine. The entire main subroutine looks like this. Okay, we have a getS here. We're getting a string, and we determine the length of the string, and then for each byte, okay, we'll go through half the array, and we'll flip the first byte with the last, the second with the second last, the third with the third last, and so on. So the array will end up, flipped. The first character will become the last one. Okay. And then after the flipping, we'll print buffer back out, and then we'll return a value of 0. So the first thing you want to know is, okay, where is it crashing? let's put a breakpoint on line 20. Now, we know that it did not crash on line 20. It did not do a segmentation fault on line 20. How do we know that? It actually printed something. Okay, it actually printed something. So we know that it's not going to crash on line 20, but let's go ahead and run it from the beginning. And then we specify a long string, press the enter key. Now we are ready to execute line 20. But instead of single stepping or using next to get into putS, I'm going to do I will inspect buffer. Okay, so I'm going to say, print buffer. And buffer looks like this, which is not right. Okay, this is not right at all. The reason why this is not right is because the input is quite a bit longer. This is the actual input. But for whatever reason, the output is only this much. Okay. Second thing we'll do is we'll take a look at the length. Okay. Length is 34, and length is determined on this line by calling string length. And if you look at the actual input, which is this bunch here, does that look like 30 characters to you? 36? Looks like 36 to me. Does anyone want to? Okay, fine. I'll do this. Copy. Go to another tab. Do a VI. Insert. Paste. And then look at the cursor position. 36. Okay, so a length of 36 is actually correct. Okay, the input string actually has a length of 36. Okay, but that means the program is behaving incorrectly because it's only flipping a part of it. It is only flipping this part, I think. And then we have the FD, and then for whatever reason, it just put a 0, which is a no terminator. And that's why when it prints out the result, it only prints up to here because whatever is after the no terminator is not going to be printed. Okay. Are there any questions? So that means whatever the bug is, whatever the defect is before line 20 for sure. All right. Well, if that is before line 20, we have a loop right before line 20. So we're going to have to debug the loop itself, which is kind of tedious. So we'll go ahead and put a breakpoint on line 18, which is the last line of the loop here. And we'll rerun the program, specify a long string here, and we'll just do a print buffer from start to finish. This doesn't look right already, does it? This is the first time we get to that line, and buffer is not long. It's not long enough. Okay, this F I kind of know where it is because it came from this F here. We have swapped the first character with the last one already. So this is what the F is coming from. SD is not swapped. It is here. The space is just this space here, and then the rest of the characters are really just whatever I typed. So whatever the problem is has occurred already. Are we doing okay so far? Now you can see, the way I debug this program is I stop where the symptom is the first time, and then I back up, right? So I keep backing up until I get to the source of the problem. How many people can run a program backwards? Because that's what you need in order to debug a program, because you are going backwards to the source of the problem, because the symptom can be very far off from the source of the problem. Okay. All right, so we know the problem has to happen, way before this. Okay, so we'll list the program. This is the for loop. This is the first invocation or the first iteration through the loop. So, well, let's put a breakpoint on line 16 then, okay, which is the first thing we do in the loop. Run the program again from the beginning, and now we are on line 16. Print buffer. We have not done a single thing to buffer yet, or supposedly we have not done a single thing to buffer yet. And yet, what are we seeing? Hey, this is not right. My input should be much longer than that, and yet I'm seeing only a part of it. What is going on here? Okay, push it back a little bit more. Push it back to line 13. Run the program again from the beginning. Give it a long string. Technically speaking, if you give it exactly the same string every single time, it's better. But I'm just being lazy and just give it a long string because I know it's the length of the string that matters. So, but let's go ahead and print buffer. It is still messed up. Back up some more, right? Okay, what is on line 13? Line 13 is here, and before line 13 we just have string length. In other words, the calculation of the length of buffer, which is not modifying buffer at all, or not supposed to, seems to be doing something weird with the buffer itself. So now we put a breakpoint on line 12. Run the program again from the beginning. Give it a long string. Now we are on line 12 before line 12 executes. Print buffer, and it is still messed up. Well, that means getS is the one that is causing the problem. Because we are right on line 12, there's nothing else that can be causing the problem here. Okay, what do you think, why do you think getS is causing this issue?
It wants to take in the string, but the space messes it up.
How much did it allocate for buffer?
Unlimited space.
No. I allocated a fixed amount for buffer. Okay, so let's take a look at the entire program. This is the beginning of May. I allocated 16 bytes for buffer. And how many characters did I type?
36.
A whole bunch more than 16, right? So from getS's perspective, it is given the address of an array that is supposed to have 16 bytes, 16 characters. And yet I'm trying to stuff 36 characters into it. So what do you think would happen? What happens to the 16? What happens after the 16 bytes that are actually allocated to buffer?
It overwrites itself.
It will get overwritten, right? So if that stuff is getting overwritten, that is the reason why we have an issue here. Because whatever we are overwriting is actually useful for the invocation of getS. But this helps us to go all the way back to the source of the problem, which is the getS instruction or function call, and it has to do with we are trying to put more stuff into the array than we have allocated for the array. Now, exactly why does it fail in this particular way? Once again, I cannot explain it here because we have not really talked about how a frame works or how it is structured. Is that kind of making sense so far? Okay. And that's about it, for today. I'm just showing you the commands in GDB that you will find useful eventually. Okay, single stepping, running, putting a breakpoint in a program, listing the source code of the program that you're debugging. All of those commands will be useful. Okay. Yes. Say that again? How does it get the data? 16 is a constant. It's a macro, so it's basically a constant.
Oh, you didn't make any next.
So that means when I run this program on line 7, it's going to allocate exactly 16 bytes for the array buffer.
Yeah, it's gonna execute.
So that buffer, that they have segments. So when you get it in out, they have segments stored there. Is that right? You have the data there.
Okay, I don't understand that part.
Yeah, for example, you have that buffer, like here, when you go back into one, then we have segments. You know where is your data, where is this also one section, where is one. But here I see where is why we have it in there, and then we can't locate it, and also one, where is that one? Every time we come out,
Done.
lost, have those segments there.
Try that.
Yeah, we can talk about
Okay,
later.
now.
Okay.
There you go.
Well, this is a fairly simple, C program. It's just, declaring an array.
Yeah.
We read in a string, and then we try to reverse the order of the bytes in the
There
string.
you go.
That's all we're doing.
Finish.
But there's one more trick to this one, okay? There's one more trick to this one, because length seems to get the right answer too, okay? Okay, let me run this program again. Just one more time, just bear with me. Okay. So we put a breakpoint. We already have a breakpoint. Okay. So right now, when we print the string out, it always prints only this much. That's because GDB understands C. In other words, GDB looks at how buffer is defined and say, hey, you know what? Buffer is only supposed to have 16 characters. That's why it's only printing these 16. In other words, if I try to print buffer in another way, it will show me the rest of that memory region. That command is called X, which stands for examine. Now, when you specify X, you have to specify how many things you're trying to print, or how many things you're trying to examine. In this case, let's say I'm trying to examine 32 things. And then you can specify what is each thing that I'm examining. You can specify a byte. Each one is a byte or 8-bit. And then you can specify how you want to print the content of the 1 byte. Now, what do I mean by printing? How do we print the content of the 1 byte? 1 byte is nothing more than 8 bits. Okay, so you can look at 8 bits as a signed number. You can look at 8-bit as an unsigned number. You can look at 8-bit as a hexadecimal number, as a binary number, as the ASCII code in ASCII code. The character represented by the ASCII code of that 8-bit. Okay, so you have a choice here. So what I'm going to do is I'm going to do a BX, which means I want to print those bytes in hexadecimal digits. Then we have to specify the address. The address is just buffer. All right. Do you find the no terminator here? There's no terminator, is there? So that means the string is actually read in. We are overwriting some important locations. We can now single step. Okay, we are single stepping into string, which is not a good idea. So I'll just continue to execute the program at full speed until we get to the next breakpoint. Now we're at the next breakpoint. We print length. Length is probably right, 33 bytes. Okay, and then we'll continue execution, and then we'll repeat the X command just to see, and this time we know there are 33 bytes, so we'll go ahead and print 34 because we want to see the null terminator. Okay. And right here, we are seeing a problem because the null terminator, seems to be here already. In fact, we find a whole bunch of zeros where they're not supposed to be. Okay, let's take a comparison. This is buffer at this point. This is buffer when they first came back. Do you see that these zeros that are now here, they were not there before? Do you see that? So we know there's a problem already. Where do you think those zeros come from?
White space?
Well, they're not exactly white space. Let's see. Let me see if I can find. Okay. some of these bytes, these bytes, which is corresponding to this byte here, those are overwritten by 0 zeros. Look at this one here. This used to be 6-1 in hexadecimal, and now it is 2-1. 2-1 in hexadecimal means we have 1 of 1 and 2 of 16s. What is 2 times 16 plus 1? 33. That number sounds familiar. What is it? What is 33? Length. LEN. And why do you think the length is here? Is it coincidental? Or did we overwrite buffer to the point that is overlapping with the length variable? Okay. Now, right here, if once you see that length is at this location and buffer is overwriting it, or it's using it as if it is a part of the buffer, suddenly things becomes clear, right? Because now we have confirmation that we have just we have not allocated enough bytes for buffer, and that's why we have a problem. And here you can fix the problem. But you will not know that problem until we learn these commands in GDB to take a look at memory locations. Now the X command in particular is going to be really useful in this class, because a lot of times when we write programs in assembly, we use pointers a lot. Okay, we'll use dereferencing a lot, and array indexing a lot. And with all of those things, unless you use the examine command, it's really hard to figure out how you are utilizing memory. Yep.
Can you explain the parts after the slash for the example?
After the slash?
Yeah.
Yes. There we go. Now, yes, but this is showing you that GDB does have internal help. It is very terse. It's not really well explained, but it is here. You just have to kind of read it carefully, word by word, because what it says is examine memory. That's what X stands for, and the format is like this: X/FMT, and then you specify the address. Now, what is FMT? FMT is a repeat count. Okay, so repeat count is a number. In our case, I used 33, 34. Okay, 34. So it's just a number followed by a format letter and a size letter. So there are two individual letters. Each one, one is representing the format, and the other one is representing the size, which is the width in number of bits. Okay. Format letters are octal, hexadecimal, decimal signed, decimal unsigned, binary, float, and so on. That's basically how do you want to interpret a particular bit pattern. But how many bits are we dealing with this particular bit pattern? It has to do with the size. So in size, we use B to specify a byte, X to specify a half word, which is 16-bit, word to mean 32-bit, G for 64-bit. So that's how you can control how you group the bytes together or not when you examine memory content. Because sometimes it's handy to look at each individual bytes, like what we are doing here, but other times it is more convenient to look at 32-bit chunks so that we can say, oh, here's a 32-bit number, here's the address, and so on. But that was a good question. I was just joking, by popping up the help. But the help screen is helpful just in case you forget one or two letters. You can just pop this up, and it will remind you how to use it. And by the way, we are not even using assembly language, and these things are already quite useful. Does anyone write programs using new and delete in C++? You would use it in CISP 430 for sure. I'm not sure about 400, okay, but 430 for sure. If you combine memory corruption with new and delete, you have something that's really interesting. Because if you mess around with how C and C++ dynamically allocate and deallocate memory locations, you can set up your program in a way where the cause of a problem is here, and the effect of that bug, the symptom corresponding to that bug, is all the way over there. Okay, and that's why C and C++ can be very dangerous, because you can end up with bugs like that. Whereas in Java, you cannot possibly corrupt your heap, because you cannot do things like what we can do in C and C++. Are there any other questions? That was a good question. Thank you. And all of these commands can also be helped. Like list, you can type help list. It will show you what you can do with list. There are quite a few things that you can do with it. Break, how to set up a breakpoint, same thing. You can help break. If you want to learn how to continue is pretty boring, but there's only one way to do it. You can supply an N, and that basically says it's basically the same thing as if you type continue 3, it's the same thing as C enter C enter C enter. It will just do 3 contiguous continue, so it will basically skip 3 breakpoints automatically. And skip step is the same way. You can specify a number, a count after step, so that it will automatically step through a few lines if that's what you want. So all of these commands that we talk about today, they have a help entry. If you want to learn all about those commands, you can definitely do so. Okay. If you're not taking any C++ classes this semester, I'm sorry, you probably won't get a whole lot of practice to use GDB. If you are, you can go ahead and use GDB or the same techniques in CodeBlocks or Dev C++, because both of those are basically just GUI front ends on top of GCC and GDB or G++. Okay, it's really just a GUI front end. The back end is still talking to just GDB. So everything you can do in those GUIs, you can do it in GDB, but it doesn't go the opposite way. Not everything you can do in GDB, you can do in the GUI interface. All right, are there any questions? No? Okay, I guess your blood glucose is really getting down there. All right, I don't want you guys to ingest yourself, so let's go home and have dinner. It's like a horror sci-fi, I'm gonna ingest myself.